keep going on this New Year's Eve. These problems are a bit harder now, so perhaps I will just go ahead and just like do a couple problems per 45-minute round. I mean, I'll do as much as possible, but let's see. Build a 4-digit counter, okay. I see. So just for my visualization, you have like the ones, the tens, like ones, and then like hundreds, and I guess thousands. And then each of these are like this, and then so basically you have counters that are like 0 to 9, and when this hits a 9, this enable is asserted to go here. When this hits a 9, this goes here, and this goes here. This seems similar to the previous problem, where you count from 0 to 9. So I'll just do this and write my own module where you have input clock, input reset, output. Count. Is this the 3 inputs? 1, 2, 3, okay. I guess they talk about Q. I'll just do count. If count is, then count is 0 else, like that. So on reset, it'll be 0, and then right after reset, it'll be 1. And then for count, we can do this count is his output. So this is actually just Q. And I can just do enable 3.1. Enable 3.1 is if Q30 is 9 and this, if Q of 7.4 is 9 and this is probably easier to just do it like this. So basically, if I'm clocking it and if I'm a 9, then I need to carry over and enable the next one. So if let's say 1 was enabled and it's already at a 9, then that means yeah. So actually this represents tens. So tens would mean that if the single digit is 9 and I'm clocking it, then that means next cycle we need to enable it. Let me think. I'm worried about a 1 cycle delay. So if a single is 9 and it's 1, then I need the next cycle to, so if it's 9 and it's 1, then let's say the tens is at 0. I'll get an input of 1 here, asserted. The next cycle, it'll deassert, and the next cycle, this will just be count plus 1. So I think that works. Plus 4, plus 4. So likewise, this would be like the hundreds. And it'll look at an enable for the hundreds. And then so if I'm hundreds and the enable corresponding to this is firing, and I'm a 9, so I'm at 900, and this this 2 is a 1. Go ahead and do it. So what would make this 2 enable to a 1? This enable 2 is made 1 when this is 9 and so it's like a carry forward. So if this is a 9 and this is a 9, and then let's say So it really starts with this one and this condition, and this informs this, which informs this. This informs this is ANDed with this to inform 2. So there's no real issue of like x's. It's just like a carry ripple from like this term and this term all the way to 3. Maybe let's run it. All right. Oh yeah, this one I already done. Create a set of counters suitable for a 12-hour clock. Your counters are clocked by a fast running clock with a pulse enable whenever your clock should increment once a second. What's a hint? Okay, well, this isn't a hint. This is like this isn't really a hint. This is a specification. Okay. So this enable increments my seconds, yes, and seconds inform minutes, and minutes inform hours. I think building this from scratch is a little easier than building like 2 modules and then 1 module, because it's just you're just doing 2 flops sort of side by side. Resets at 12 a.m. I assume synchronous reset. Oops, wrong language. If enable begin end. Thought I was doing TypeScript. If enable, go ahead and then do SS is gonna be if SS is 59, then SS is 0, else SS plus 1. So this is the same as this, right? So if SS carry means 59 seconds and enable, that means in the next enable, we need to carry this S into the M. So this SS carry says, hey, I need to turn over a new minute. So if I need to turn over a new minute, just go ahead MM plus 1, unless it's 59. And then if it's 59, then it's, you know, like this. 0, if it's 0. Now if minute 59 and SS carry, that means it's minute 59, second 59, and there's an enable, so we need to turn over an hour. And then so if MM carries, then go ahead and do PM is what? PM is we start at 12 a.m. 12 a.m. is 0. So we need an hour carry. If it's 12, if it's 12, we go back to 1, and then like that. Is when X is on hour 12 and MM carry. If it's MM carry, then you know that means it's hour 12, 59, 59. Actually, it's like this. $11, 59, 59. Then we flip the PM. And likewise, if it's 11:59, 59 PM, then we flip to AM. Then, if Actrix Carry, then just go ahead and that. See if this compiles even. Maybe let's just double check. Mm-hmm. 59, 59, and enable means we're going to flip it 11 to 12. Anytime 11 to 12 we flip it, but then 12 back to 1. These two have the same code line, and the numbers are the same. These are like X. The only thing that's different is that we're instead of 0 to 59, we're going to 1 through 12, and this is powered by this minute carry. This is we increment the minute powered by the second carry. This is just powered by this enabled signal, and if we reset, we're at 12:00 a.m. And then if we have this hour carry, which is 11:5959, then we flip the PM. Did I PM instantiated here? Oh. I see. That's annoying. then I'll probably just do this then. Actually use the deck count. I see. That's their way of encouraging you to use this thing. Okay. So this is seconds, and if I enable, then I'll have like ones and tens. I also want to reset it if and what? Enable it when kind of messy, but you get the point. So basically the 0th here represents the single digit of seconds, and it counts from 0 to 9. And so if we have a second increment which is enable and it's at 9, then we want to enable the count of this digit, and if this digit so we'll keep doing that, but this digit would count up to 9 otherwise. So instead we want to reset this top digit back to 0 at 5 if it's basically if it's SS carry. SS carry meaning, you know, we have this, basically this condition. And so this condition, and then also if I'm at the 5th, so I'm at 59 seconds and I'm enabled, then that means I'm going to turn over a new minute. When I turn over a new minute, I need to reset this 5, go back to 0, and then the LSB9 will already go back to 0 because it's 9 and enable already. Now, that should take care of SS, so I don't need this anymore. Likewise, for carry, we can do something similar. So, except SS carry is the thing that increments this. So we go here, and then this will increment our minutes. And if we increment our minutes while if we're at like the 9th minute, then, and we're incrementing that we need to carry over, like, so that, you know, we go from 9 to 1 successfully. And then this will just be carry meaning we're at 59 minutes. 59 minutes, 59 seconds, and enable, basically. Then we'll reset this. And then the Actrix Carry is going to be for D1, 41. Carry, like this logic remains the same. Now I don't need this anymore because this takes care of our Okay, powered by SS carry as an incrementer on both ends, the digit and for the tens, and then to reset the tens going from 5 to 0, we just do this carry qualifier. Lastly, we have this Actrix carry. So carry says we're turning over a new hour. So whenever we turn over a new hour, we do this. Actrix is tricky because it's like, it's not a 0 to 9 counter, it's a 1 to 12 counter. So let's just do like 1 to 9. So generally speaking, if we're turning over the hour, we just keep it unless it's like 9 to 10 or 12 to 1. So if HH is then this needs to be 1, so 9 to 10. Otherwise, if there's no 19, because if it's 12, meaning HH so I'm at the 12th hour and I have this hour increment, then I must go back to 0, else keep my original time. And then so notice here that this is, if we go to 9, then that means we're at 0 like this. But if this condition, then actually the single digit, we go from 2 back to 1. So HH like this, otherwise that. This is probably the most tricky one. Actrix Carry is straightforward. This is just saying, you know, this is the same logic as before. So I think PM is okay. This part is the tricky part. So if I'm 9, I will go to 10, which means it's 0. But if I'm at 12, then the single digit flips back to 1. And then this will prevent me from going to like more than 12. Because this and this combined means that it'll go back to 0, 1. And otherwise, I'm free to increment this single digit normally when I have a hour increment. So then I would go from 1 to 9 to 0. When this goes to 0, this goes to 1. So kind of like an abacus, 1, 0. So this is 1, but then we keep doing this until we hit this, and then we set it back to 1 and 0. So I think that's okay, but that's a lot of code, so. So I have multiple drivers for SS and MM. Oh, because of this reset. This reset is handled here, so SS and MM are handled there. But for our, there's no such internal structure, so we need to handle the reset here. And PM as well. Let's see. Yeah, these counters are quite hard. Oh, if yeah, if we're at hour 12, the single digit goes back to 1. Not sure how I deleted that, or maybe My reset doesn't seem to be working. I see. All right. Yeah, this one was, I guess, hard because of this tricky thing and this tricky thing of the BCDs. And yeah, it's just kind of like a lot of bookkeeping going on, I guess. All right, let's see if we can do a couple more. Because I know like these sections start out fairly basic and then they just kill you. Build a 4-bit shift register right shift with asynchronous reset, synchronous load, and enable. What is load? Verilog. Load means force some data in. Okay, sure. Loads shift. Okay, I see. And then a reset. Yeah, so I guess I don't know, like, because in the other problem I got confused about the load is an output. So load makes sense here. Load is like force and input. All right. Okay. I like this spec. This spec makes sense. So this is asynchronous reset, and then with this asynchronous reset, we reset this to be 0. Otherwise, what do we do? If load, reset must take precedence, right? So, and then load would take precedence, and then enable. Yeah, enable. Hey, I solved 100 problems. And then I need to rotate 100 after I solve the 100th problem. With a 100-bit left-right rotator, okay, with synchronous load and left-right enable, okay. Shifts in the shifted out bit. Okay, so it's a rotating shifter. If enable or rotator rotates the bits around, does not modify or discard them. Load the bit. Instead of rotating, enable rotates left, rotate right. Okay, not too bad, I think. All right, 2 minutes. What about reset? Synchronous load, if load. Then Q is just data. And then if enable is 2-bit 01, else if enable is 2-bit 10, then Q is rotate to the right, which means that a rotating right shift. So then this is Q0, and then Q to the 99.1. Likewise, here we would have Q to the 98.0, Q99. If I am not mistaken. Nice. Okay, that took 2 minutes. Build a 64-bit arithmetic shift register with synchronous load. Shift in the sign bit instead of 0 as done by. Okay, sure. Yeah, I can finish this problem to wrap it up. And what is this load? Synchronous load. That's easy enough. And if I'm not loading, then I can actually allow this to happen. Enable. So basically, if enable and so this or this, then I'll just use the amount 1 to see if I'm left or right shifting. So if I'm this, I shift by right, then I will just do so this is this sign extension. And otherwise, I'm shifting left by 1. So then this means I'm shifting left or right by 8 bits. So this will be very similar. Handling this case, let me just double check that. So 0 is shift left, so 1 is shift right. And if I'm shifting right by 8 bits, then what is this? This is just math. plus 62 is... No, it's just this. If I right shift by 7, then, you know, 7... Sorry, if I right shift by 8 bits, then 7 to 0 vanishes. It gets shifted out. And then I just sign extend by 8. And to the left, you know, to the left, we do 8. Okay. This is 1. And left shift is the same. All right, that's it for this sort of like 45-minute round. I'm actually glad these are getting a little harder, and I'm also quite glad these few problems, the specifications are much more like on point, where they actually define what the signals are. So anyway, that's it for this one.